Right, so let's have a look at question 4, which is looking at the photoelectric effect but in a different way. So we have a metal cathode here being illuminated with white light, and it's currently going through a blue filter. So it asks you to explain why no photoelectrons are emitted when the blue is replaced by red. So, key things to know about red is that the wavelength of red is higher than that of blue. And that would mean, therefore, that the frequency of red is less than blue. So that's the first point you would need to make. The next point would be showing, therefore, energy is HF. So if the frequency drops down, the energy of the photons is lower. So that's another one. And then, so the concluding statement is if there's no emitted, that must mean that the energy is less than the work function, so no electrons are emitted. So those are the three stages. You could get 2 marks here by lumping this stage together by saying the frequency is less than the threshold frequency, but that's not giving a detailed enough explanation. What you want to do is link frequency to energy and then energy to work function, and that gives a complete explanation of how this works. Okay, so you've got metal of work function 2.3 times 10 to minus 19, and ultraviolet radiation of wavelength 200 nanometers. So what's the frequency? So frequency is the speed of light divided by the wavelength. So it's going to be 3.00 times 10 to the 8 divided by 200 times 10 to the minus 9. And if we stick that in our calculator, both numbers are 3 significant figures, so we should give a 3 significant figure answer. And we get a value of 1.50 times 10 to the 15 hertz. And it wants the threshold frequency. So remember, the threshold frequency is the work function divided by Planck's constant. So it's going to be the 2.30 times 10 to the minus 19 divided by the value from your formula sheet. And when we type that in, we end up with a value of 3.47 to 3 significant figures times 10 to the 14 hertz. So that's a frequency as well. So we've cracked that one. So let's flick over. And it wants the maximum kinetic energy of the photoelectrons. So the max kinetic energy is when you have the photon energy minus the work function. So it's going to be 6.63 times 10 to the minus 34 times by the frequency, which is 0.50 times 10 to the 14 minus 2.3 times 10 to the minus 19. Actually, that was 2.30, so let's not lose significant figures. Let's type that one in. And then subtract the work function. And we end up with a value of absolute nonsense. Why have I got nonsense? Oh, I've made a mistake. That should be 15, not 14. Let's type those numbers in again. And you end up with 7.65 times 10 to the minus 19 joules. So that will conclude question 4. Question 5 is pretty quick, so I'll just continue straight on. So we're looking at the wave properties of particles. So this is governed by this equation here. So we need to rearrange it for this question. We want velocity, so that's going to be Planck's constant over m lambda. So we'll have 6.63 times 10 to the minus 34. God, I feel like I've written that out millions of times, but never mind. We've got the electron, so the mass of the electron is in your formula sheet, so times 10 to the minus 31. And then the wavelength is 3.2 times 10 to the minus 8. And we'll type those in. Minus 31 times 3.2 times 10 to the minus 8. And we end up with 2.3 times 10 for 4 meters as the wavelength there. As the velocity, so it's meters per second. And then we want the wavelength, that's going to be h over mv. So one final time, here we go. Woo, done. We've got the mass of a proton, minus 27. It's 27, not minus 37, times by 2.27, yada yada, times 10 to the 4. And we'll calculate that as 1.7 times 10 to the minus 11 meters, because it's a wavelength there. So then it's asking what kind of experiment would confirm that electrons had wave-like nature. So this would be the electron diffraction. So you would use a double slit to do it, but the way to describe this experiment is electron diffraction, and that concludes the videos reviewing the recent assessment.